Uh, Hello everyone. Uh, in this video, I'll be talking about I will be talking about this notebook, which is a masterclass on making neural networks generalize better. Uh, that is, perform well on new data that haven't been seen before, and not just on training data. So it is so for this there are mainly two main families of techniques. The first is regularization, and then another one is augmentation. So regularization it prevents the model from memorizing the training data, which is overfitting, and whereas data augmentation is a trick that artificially expands your data set so the model sees more variety of data. So yeah, in this assignment, every major technique is demonstrated as an A/B test. So basically, train one model with the technique, one without, and then compare the learning curves side by side. So let's start. So initially, we are doing some setup and imports. Then comes the L1 L2 regularization. So the problem it solves is, without any regularization, a model can develop very large weights that perfectly normalize the training data, but fail on new examples. So what L2 regularization does is it adds a penalty to the loss proportional to the square of each weight. So the weights are pushed towards zero gently. So no weight gets completely eliminated, but all stay very small. So in PyTorch, this is built using the Adam optimizer using weight TK. And whereas L2 adds a penalty proportional to the absolute value of each weight. So this tends to push some weights all the way to zero. So like in L2 it just reduces nearer to zero, but in L1 it will completely push the value to zero. And yeah, in PyTorch this must be added manually inside the training loop, since optimizers don't have the built-in L1 option. So yeah, the notebook trains 4 variants, which is like no regularization, L1 only, L2 only, and L1 plus L2 together, and all the 4 plots are here. You can see all the 4 are plotted over here, and you can see the curves are the behavior of curves very differently. So the last two are no regularization and on L2 train. So on L2, basically shrinking the value towards zero, it worked really well. Whereas the performance of L1, just L1 and L1 plus L2 was kind of wobbly. So this is the final output. Yeah, these are the best value accuracy. So no regularization was 44% accurate, whereas L2 was 42, L1 42, L2 43, and L1 plus L2 is 42.5. So it means the L1 L2 regularization did not make much of a difference, like it reduced the performance only. So yeah. Then we have the dropout. So the idea is, during training, you randomly switch off a random fraction of neurons on every forward pass. So this forces the network to learn redundant representations, and it can't rely on any single neurons too heavily. So here we have different types of dropouts. Zero is no dropout. 0.2 is it means 20% chance of being zeroed out. Each neuron has 20% chance of being zeroed out. This has 40% chance, this one has 60% chance. So we will be doing the A/B test on all 4, and here you can see the comparison, and you can see how the aggressive dropout affects learning. So Then we have early stopping. So the problem is, if you train for too many epochs, the model starts fitting noise in the training data, which is overfitting. The validation loss starts rising even as training loss keeps falling. So early stopping monitors validation loss each epoch. So if it doesn't improve for, like, for patients, let's say 5, the training stops and the model weights are reset to the best checkpoint it saw. So the notebook it compares 80 epochs without early stopping. Likely it will be overfitting versus 80 max, 80 epochs max, and with the patience equals to 5, which means it stops much earlier. So this here you can see that the blue and the orange line are without early stopping. So here you can see the training loss. Even though the training loss is decreasing, the validation loss is increasing. This is the main grokking situation, and we don't want to do that, because it means that the model is overfitted on the training data and it's not working well on the unseen data. So this is where we want to stop our epoch. And once it's it will stop at a very sweet spot. It will find a sweet spot and just stop it. And yeah, rather than giving a very weird accuracy, it will stop. Yeah. So that is early stopping. Then we have Monte Carlo dropout. So this is a clever trick for getting uncertainty estimates out of a neural network. So normally a trained model gives you one confident prediction, but what if the model is actually unsure? So Monte Carlo dropout runs the same input through the models many times. Uh, Here it is 50 passes with dropout still active. So each time dropping different neurons. So the spread of the prediction tells you how uncertain the model is. If the predictions are very similar across all 50 passes, the model is confident. And if they vary, it means the model is uncertain about this input. So this notebook visualizes this uncertainty as a heat map. So the trick in code, is forcing dropout to stay on even at inference time by using the f dot dropout and instead of just model dot train. Then we have the weight initializations. So why it matters is neural networks start with random weights, and if those starting weights are too large or too high, we can have the problem of gradient explosion or vanishing during training, and the model will never learn well. So the notebook demonstrates 6 strategies. So K-Ming init, Xavier init, orthogonal, and normal. So the K-Ming is designed for ReLU activations and it scales the weights based on Fanon, whereas Xavier, it is designed for Stan and Sigma activations and it balances fan in and fan out. Orthogonal, on the other hand, preserves gradient magnitudes and it is popular in RNN. And the normal is a naive, very standard normal random weights and is often too conservative. So each is tested by looking at the first epoch training loss, and a good init means learning fast from very beginning. So here you can see the performance of the loss and the accuracy of all the 4 strategies I mentioned. Then we have batch normalization. So the problem it solves is, as the data flows through layers of deep neural networks, the distribution of activation can shift drastically. So later layers have to constantly adapt to the shifting input distribution, slowing training. So like batch norm 1D or batch norm 2D normalizes each batch of activation to have mean like similar to 0, around 0, and standard deviations as 1, and then applies learning, scale and shift parameters. An important nuance over here is when batch norm follows a linear layer, you should get bias equals to false on that linear layer because the bias is redundant, and batch norm's own shift parameter replaces it. So the notebook compares the three variants of no batch, batch norm before activation, and batch norm after activation. And here you can see the loss and accuracy of it. So here you can see the batch norm before training worked really well. Then we have custom dropout and custom regularization. So this section goes beyond PyTorch's built-in tools and implements several advanced variants from scratch. Which the first one is Gaussian dropout. So instead of hard zeroing neurons, multiplies activation by random noise centered at 0, and this is smoother than standard dropout. Then we have drop block, which is drop entire contiguous block of neuron rather than individual uh, random individual ones. So this was developed because of the convolutional networks, and nearby neurons often carry similar information. So dropping isolated individual neuron doesn't help here. So yeah. Then we have stochastic depth, which is random. It randomly skips entire residual branches during training, and it is used in modern architectures like ResNets and vision transformers. Then we have orthogonal regularization, which is it adds a penalty that encourages a layer's weight matrix to stay orthogonal. Orthogonal matrices are good because they don't distort the scale of activation. Then we have max norm constraint. So after each gradient update, the clip update clips the weight norms of no single neuron's weight can grow too large. So and applied as a pre-processing step after the optimizer.step function. Then we have TensorBoard and callbacks. So TensorBoard is a web-based dashboard for visualizing training in real time. So the summary writer log metrics like loss, accuracy, and learning rate, and weight histograms to disk. Then you launch the TensorBoard server to view them. So this section also implements the callback style pattern in the pure PyTorch. And so we have LR scheduler callback. So it reduces the learning rate when the validation loss stops improving. Then we have warm-up scheduler, which is it starts with a very low learning rate and ramps it up over the first few epochs and then applies cosine leaning decay. Then we have a model checkpoint, which is it saves the model to disk whenever the validation loss reaches a new best, which we just saw in the early stopping. Yeah, here you can just see and change the values. And then we have Optuna hyper parameter search, which is manually tuning hyperparameters. So like hyperparameters like learning rate, dropout rate, number of layers, etc. And it can be tedious. So Optuna automates this. So you define an objective function that builds and trains a model using hyperparameter values suggested by Optuna, then returns a score, which is validation accuracy over here. So Optuna runs this many times, intelligently choosing which parameter combination to try next based on the past results. The sampler used here is TPE, which is tree structured tree structured Parison estimator. It's a Bayesian method that's much smarter than random search. So the median pruner kills trial early if they are performing below the median of previous trials. So it saves time. Um, then we have torch vision data augmentation. So this section builds a comprehensive image augmentation pipeline using Torch Vision's newer transforms.v2 API. This one. Yeah. So it has functionalities like random horizontal flip, which mirrors the images left to right. So yeah, as I mentioned earlier, right? So there are two techniques to tackle overfitting, which is regularization and augmentation. We just looked at the various steps at regularization. Now we are looking at the augmentation. Augmentation is just adding more data, more variation of your data in your data set, so that model learns different variations of your data as well. So yeah, the horizontal flip. Then we have random crop, which pads then crops to a random position, introducing a slight translation. Then we have color jitter, which randomly shifts brightness, contrast, and saturation and hue. Then we have random grayscale, which is it occasionally converts to grayscale. Then we have random erasing, randomly blacks out a rectangular patch, a technique called cutout. Then we have cut mix, which is it blends two images. It blends two images and by cutting a patch from one and pasting it on another, mixing labels appropriately. Then we have mix up, which blends two images and their labels by weighted average. So now there is like we did a A/B test showing the training a CNN with augmentation and without, and here you can see the loss and accuracy for it. Here you can see that no augmentation, without augmentation, and this augmentation train, and without augmentation, this is the validation. You can see the validation score is going down even though the train values are going down, but the validation loss is increasing. So we don't want our model to do that. Here you can see the green and the red line, they are working together. That means the augmentation really helped in the training. Then we have augmentation across 7 data types. So this final section extends augmentation to domains beyond images. So we have 12A. 12A is classification with the RESTnet style architecture. So a REST block adds a shortcut connection, and so the input is added to the output, which helps very deep neural networks train without vanishing gradients. Then here you can see the performance of it. Then we have video classification using CNN plus LSTM architecture. So each video frame is passed through a CNN to extract features, and then an LSTM processes a sequence of frame features to capture temporal patterns. You can see the values here. Then we have text or NLP using NLP org for synonym replacement and word deletion and simulated keyboard typos. The two model architectures are compared, text LSTM and text CNN, which uses multiple parallel 1D convolutional to capture 1-gram patterns. You can see. Then we have time series augmentation signal with jitter. So we are adding small random noise and some random scaling. And 1D CNN classifies synthetic sinusoidal signal of a different frequency. So this is the accuracy for that. Then we have tabular data using SMART, which is synthetic minority oversampling technique, to handle class imbalance by generating synthetic examples of underrepresented classes plus Gaussian noise and random features masking as augmentation. Here is the performance for that. Then we have audio and speech converting raw audio to MEL spectrograms, a 2D visual representation of frequency over time. Then applying spec augment, randomly masking time and frequency band before feeding into 2D CNN. Then we, yeah, uh, then we have this document image augmentation and classification. So document images generating synthetic in voice, receipt, form, or letter images and augmenting them with rotation, blur, brightness, jitter, and random erasing. So it includes an OCR demo using Tesseract to extract text from the images. Yeah. So that is it for the for this notebook. Thank you.